I want to talk about Euclid's algorithm. Now, this is a very powerful tool in number theory, and it reflects something fundamental about division and remainder. Now, the main idea is very simple. If you want to find out the GCD, that is the greatest common divisor, or in some countries this is known as HCF, the highest common factor. If you want to find this, one way is to prime factorize the two numbers. So let's suppose I want to find out the GCD of 10 and 15. I would prime factorize 10, so that's 2 times 5. I'll prime factorize 15, that's 3 times 5. And I'll look into the common stuff. So, of course, I am saying colloquially, this can be formalized, but the common thing is 5. So, okay, that number becomes the common divisor. Now, by taking in as many common stuff as possible, you'll find the greatest common divisor. So this is one way of finding the GCD. Now there is another way, and that is sometimes more useful. So there is another way, and that other way is called Euclid's algorithm. And let's use the same example to illustrate what's going on. So suppose we have 10 and 15. Step 1, so it's an algorithm, so there will be step-by-step instructions of how to do this. Step 1 will be take the larger number, so pick the larger number. In this case, this one is 15, so the larger number is 15. Because if the two numbers are same, their GCD will be that number. So the GCD of 10 and 10 will be just 10. So if they are not equal, only then you have to compute the GCD. So pick the larger number, which is 15 in this case, and divide it by the smaller number. So let's call this larger number L. We will think of this as a black box, or in this case a golden box. We will update the value of the box or the number in the box in each successive step of the process. So right now in this golden box we have the number 15, which is the larger one. Step 2, divide the number inside L. So remember, L is just the name of this larger box. So the number inside L is 15 by the smaller number. And let's also, before even doing that, let's put the smaller number in another box. Put the smaller number in another box, in a white box. Let's call it R. So we have two numbers. In fact, we have two boxes, R and L. This first box contains the larger number. The second box contains the smaller number, which is in this case 10. And we want to divide the number inside L by the number inside R. So let's do that. It's 10 times 1. So this one is the number inside L. This one is the number inside R. And this is the quotient. So let's call it Q. And we have a remainder, which is 5. So this is the remainder. So the step 2 of the process is done. What is step 3? Well, in step 3, we will put remainder inside the R box, which is in this case the white box, right? So we will be putting the remainder 5 inside this box 10, which contain 10. So now the white box contains 5. So you understand this R is actually a variable. That's the meaning of the word variable. You should think of a variable as a box whose value you can update. So a variable is a box whose value or the number contained in the box you can update. So in this case we updated, so it contained 10, now it contains 5. So we erased 10 and we put 5 in the box. Okay, all right. So I'm doing this very slowly because these are two very simple numbers. We don't really have to even worry about the GCD. We can easily find it like this. But if the numbers are too large, let's say two numbers, one of them containing million digits, another containing a zillion digit, how would you find the GCD? So this method will work for any pair of numbers, and you don't even have to prime factorize it. Now let's go to step 4 and divide and put, okay, first put the number inside, or the smaller number from step 2 inside the larger numbers box, so inside L. So now this particular thing contains 10. From step 2 the smaller number was 10, so you have put 10 inside the large inside the box L. Okay, in fact you could do this step first and then you could do this one. That would be actually better. Anyway, it doesn't really matter. Now, so you have this. So now let me write the situation. So you have 15 in the box L and 10 in the box R. This happened in step 1. In step 2, you put the number inside this box inside L, and you put the remainder inside R. So the remainder that you get by dividing 15 by 10. The remainder that you get by dividing L by R. This one. Okay. So you put the remainder inside R. Okay. Now you do the same process again. See, in this case, the remainder, the next step, the remainder will be 0. Right? Because 5 exactly divides 10. Then we will say that the process terminates in step 2. So let me write that. The process terminates in step 2. Why? Because in step 3 we are getting a 0 in the place of the remainder, and we cannot divide by 0, right? So we were dividing. So if we wanted to do another step, what would happen? You would put 5 here and you would put 0 here, the remainder, but you cannot divide anything by 0 because 5 by 0 is not defined. You are dividing L by R to find the remainder in every step. This doesn't work because the division by 0 is not defined. So the process terminates in step 2. And this one, the last R that we have got, that is the GCD. So this is exactly what Euclidean algorithm is, and I wrote this in the form of an algorithm so that you can really instruct a computer to do this. But the internal logic of the algorithm is also fantastic. You should understand that. Of course, the main question remains why this algorithm works. What is the mathematics behind this? Why this algorithm works? So before even we do that, let's take another example. Let's take the two numbers 36 and 42. And let's find the GCD of 36 and 42. Find their GCD using this algorithm. So what is the step 1? Make two boxes. Step 1, make two boxes, L and R. L contains the larger number, R contains the smaller number. So then in step 2, we will update the values of these two boxes. So we will put R inside it, the smaller number inside L now. And then inside R, we will put the remainder. So we divide 32 by 46, 42 by 36, and the remainder is 6. So 6, that's the remainder. This is step 2. Step 3, we again put 6 inside this larger box L, and R should contain the remainder. So 36 equals to 6 times 6 plus 0. So the remainder is 0 here. So we have reached 0. So the process terminates at step 2. Process ends. And we can say that this is the GCD. And indeed, the GCD of 36 and 42 is 6. You can do this using prime factorization as well. Question is, can you instruct a computer, create a step-by-step method and instruct a computer to actually do this for arbitrarily large numbers? And you can. I mean, there are only 4 steps of this process. Step 1, step 2, step 3 and step 4. And then after step 4, you can tell the computer to go back to step 1 or rather go back to step 2, whatever. That is, go back to the division step. So we will come back with a new video on why this algorithm works. But for now, you can go to the link in the description. To try some more examples. Okay, and I'll come back with a new video on why the algorithm works and also how can we use larger numbers as examples. Okay, thank you for watching. Take care.